Well, good morning. Sorry, I've had a coughing spell. It's 11:42 now. Sorry, we're 12 minutes late getting started. It's supposed to be linear algebra math 237. Unfortunately, I'm the only one in the room right now, so sorry that I'm late getting started, but everybody else is later. I was registering a student and lost track of time, and then, or advising a student and lost track of time, and then I came up here, no one was in the room, so I went down to try to clear my head, and it didn't do any good. I'm still really congested. So anyway, hopefully somebody will be coming in, but until then, I'll go on and get started with where we left off last time. Now, according to my mark, and I thought we had already done that, but I guess we didn't, here's some, sorry. We talked about the sum of two vectors. I know we did that in Rn. And we talked about scalar multiples of a vector in Rn. Those two operations, sum of two vectors and scalar multiples, are called the standard operations in Rn. And here's how we define them. It's pretty close to what we've done before, but this is for Rn as opposed to R2, which is, I know what we did that one before. So let's do it for R superscript n, okay? Let vector u now I'm going to always tend to put angle brackets here, but this book uses parentheses. These are the components of u in n space. So that means it's going to have n components. It'll have a u1, it'll have a u2, it'll have a u3, and ... all the way up to and including u sub n. N components in n space, like 3 components in 3 space, 2 components in 2 space, n components in n space. Okay, and you also have a vector v, which is also in n space. Okay, so it's going to be v1, its components v1, v2, v3, and all the way up to and including v sub n. Can't have any more, can't have any less, has to be exactly the same size as u. Okay, they're both in Rn. Elements in Rn, whatever n is, 3, 2, 7, 14, whatever. And we want C to be any real number. Okay, now that's the real number system. Okay, a number in the real number system. Sorry, we're using R for both of those, but in the real number system. Okay, then the sum of u plus v would be defined just like we've done it before. You add the first components, u1 plus v1. That will be the first component of your sum vector. You'll have u2 plus v2. Add the second components together, u3 plus v3. Add the third components together and keep doing that up until you get to u sub n plus v sub n. And that will be the sum vector, just like we've always done it. Scalar multiple. Okay, scalar multiple of the vector u by the scalar c would be c u. Okay, you could have used either u or v. And this would be cu1, cu2, you multiply c by every component in the vector. cu3, ... all the way up to and including cu sub n. Okay. Now, good. Thank you. You're here. What's that? Yeah. Sorry. Sorry. The cold's much better, but now it's settled into a pretty aggravating cough. So plugged in, so let's see if I'm projecting. I didn't go over any announcements because nobody was in here. And really, I don't know of many. I know there's some out there that I haven't printed or haven't seen, but I can't remember what they are right now. Some of them I haven't seen. I wouldn't know what they are, but the ones I've read but didn't have a printer at the time, so I didn't get to print them off. But maybe sometime or another I'll have time to sit in my office and get caught up on things like that. But right now, it's not happening. All right, now, but one thing that hopefully is completed now, may not be, but hopefully it is, or at least mostly completed. We have been having our SACS accreditation visit this week, Tuesday, Wednesday, and it went through today anyway. Every 10 years, okay, SACS is Southern Association of Colleges and Schools. They're the accrediting agency for the southern states in the U.S. Okay, now I don't know how far west that goes, but at least I know it goes at least through Texas. So everything from the East Coast, at least through Texas, it may go further, and somewhere, I don't know how far north it goes either. But that's, and at least once a decade, you have to get re-accredited. And we've just been through our re-accreditation process, okay? We started it well over a year ago, and I've been working at it. If you've noticed in the hallways, all these signs about QEP, Quality Enhancement Plan, Race for the Finish, retention, advising, completion, and engagement. That's our big push this year. And then there's all sorts of other paperwork you have to do. We've submitted the paperwork months ago. They've returned comments on some of it, and I think we've made all the corrections and met their comments and sent it back to them, probably months or weeks ago. And then this was their visit, site visit, where they come and make sure we are indeed doing what we said we were doing. And our QEP is what we've got planned and planning on that. So, anyway, today, this morning, 8:30 was supposed to be, I think, the final meeting. They were going to meet with all the people involved and give the report. I don't know what's happened with that. That was over on the Birmingham West Campus in the ACAT building, so I have no idea. I bet you it went well. All indications were everything was going well. But at some point, maybe already, they're off the campus, okay? But if they're not, they won't be here much longer. And hopefully they didn't have too many things they gigged us on, and hopefully we can get those cleared up pretty quickly and easily. But anyway, if it's not over, it's close to being over. So I don't think you have to worry about running into them anymore or anything else. But if you do see a crowd of important-looking people walking around, they may still be here. But I don't think they'll be here past today. I doubt if they're even still here. I imagine they've gone. But I don't know that for sure. That's the only major announcement I knew about. But I did have a question in a class yesterday, so let me go on and discuss that now. Sorry. So sorry. We are far enough along that we can sort of start talking about our end game here. We have class today, of course. We have class next week. Okay? Then the following week is Thanksgiving week. Y'all have it off the whole week. We are going to be here Monday, Tuesday, and Wednesday. Or at least most of us will be. Some of them will be going down to Montgomery for the statewide meetings. Those that are still here, including me, will be over on the Birmingham West Campus Monday and Tuesday anyway. And we have local, what they call professional development. Okay, now I also have 2 eye appointments, one Monday and one Tuesday. But I'll be coming to campus after my eye appointments are over. The first one may take a few hours, they said. The second one won't take long at all, they said. So I'll be on campus Monday and Tuesday, but it won't be at the beginning of the day. It'll be later in the day. Tuesday, hopefully later in the morning. Okay, but anyway, that's Monday and Tuesday. Wednesday, usually they let us back to our offices, and so I'll be in my office on this campus on Wednesday. And the school will be open Monday, Tuesday, and Wednesday. It's closed Thursday and Friday for Thanksgiving, but it is open Monday, Tuesday, and Wednesday. But here's what I tell students. Don't plan on getting too much business taken care of Wednesday afternoon, because usually Wednesday afternoon, day before a major holiday, no students here, they usually start letting people go a bit early. Now, they don't always, and they don't have to. So I've seen it. It seems like sometimes as early as noon. Usually it's sometime later in the afternoon, like 1 or 2. But I can almost bet you there will not be many offices still open at 5 o'clock on Wednesday. So don't postpone any business you have with the college until late Wednesday. Get it done Monday or Tuesday or Wednesday morning. That's the safest. You can try Wednesday afternoon, but the longer you go in the afternoon, the less likely you are to find anyone present. Okay? Then, after Thanksgiving week, we're back on campus for a week of classes. And then the following week is final exam week. So we basically just have 2 more weeks of classes and then finals.
I was wondering about that because we have the syllabus. I said we still have a lot of material of chapters.
Okay. Actually, seldom have I gotten out of chapter 4. So don't sweat that. Yeah. So this is just, it's most of the time it's material that's too new for people to gobble it up that fast. So we get as far as we can. Basically, I think maybe one time I've gotten into chapter 5. But I have never gotten, I don't think, beyond chapter 5. So don't sweat that. We'll get as far as we have. My guess, chapter 4 test will be the last test. It'll be your final exam. It'll be take home. So whatever we get to cover through on that first Thursday in December, we have class Tuesday and Thursday that week, I'll give you your final exam that day, and you have anytime the next week to get it back in. Okay?
Yes, sir.
All right. And we'll get as far as we can. Now, I was just going over where we left off last time, and I know you weren't here last time. We got started in chapter 4, which is vector spaces, which I think is probably the biggest and maybe most important block of what's left. Okay? Then we'll do, if we get into 5, those are called, is what? Eigenvectors? Yeah, eigenvectors, no. Okay. Chapter 5 is inner product spaces, I think is what it's called. Yeah, inner product spaces, which builds on vector spaces. So whether we get there or not is not sure, but we'll get as far as we can. Now the eigenvectors, I'm not sure I've never gotten quite to them. Let's see how close we're going to get. No, they're chapter 7. Okay? Never made it that far. Okay? So if we do get that far, fantastic. But I don't think we're going to make it. So let's just deal with vector spaces now. And frankly, we haven't even defined what a vector space is yet. What we've been talking about so far in chapter 4 and 4.1 are vectors, vector operations, and now we're moving to vectors in space. Now, do you know what I mean by in space? Okay. One-dimensional is just a straight line. Okay? And that can be a vector. You can either go that way or this way. There's only 2 choices. Okay? That's a vector in one space. 2 spaces is a plane. Any plane. Desktop, any plane. And then you have 2 dimensions. One this way, one that way. Okay? Usually horizontal, vertical, or however. Okay? That's vectors in 2 space, or R2. R superscript 2. Okay? and that would be in the plane. And that's what we did up until this page that we're on now, up until page 148. Okay? Then there's 3 space. That's what I call it. R3. R superscript 3. That would be the root. That would be space as we know it. X, Y, and Z. 3-dimensional. And you can have positive, negative. Yeah. Now, anything beyond that, I can't visualize because I live in 3 space. I can visualize things on 2 space, but I can't visualize things in 4 space. But we're doing in space, any dimension. And as far as vectors are concerned, they don't care if you can visualize them or not. It's just a principle. Now, if you're in space, and we are in this is the definition of vector addition and scalar multiplication in Rn, R superscript n, and that's on page 149 if you've got a book. And this is what it's saying. Sorry, I'm having drainage issues. Okay. What if you have a vector u in space? Now, what does that mean? That vector u has n components. In one space, you only have one component. It can be plus or minus, but only one component. In 2 space, you can have an x and a y. Okay? 2 components. Or you could call that u sub 1 and u sub 2. Whatever you want to call it. In 3 space, x, y, and z, 3 components. In space, you have n components. So this vector u has a component in direction u1, u2, u3, all the way up to u sub n. Okay? Now vector v must be in the same space, and if it is, it has n components. 1, 2, 3, 4, 5, 6, up to n. These are vectors in Rn. Okay? And we also have C being a real number. Now, that R is a spatial thing, space, R space. This is the real number system. So I'm trying to make them different looking R's. I was just too lazy to write out real numbers. Okay. Now, to add 2 vectors in space, they're both are n-dimensional vectors, then you just add them component by component by component. u1 plus v1 would be your first component, u2 plus v2, second component, u2, 3 plus v3, third component, and all the way up to u sub n plus v sub n. That would be how you add vectors in space. Okay? Scalar multiplication in space, you're multiplying that real number c, any old real number in the world, by either one of the vectors they chose u. So that means you multiply c times u1, component 1, c times component 2, c times component 3. Do that all the way up to c times component u sub n. Okay? That's how you do scalar multiplication. Now these 2 operations are your standard operations in space, or Rn. I usually just say Rn, but you could say in space. Now, as was true in 2 space, and certainly 3 space as well, you have a negative of a vector in Rn. So now this is not in the definition, this is something else. You can do negative u using that same definition up here, which would then be minus u1, comma, minus u2, comma, minus u3, comma, dot, 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 all the way up to and including minus u sub n. You just negate every component. You're heading in the opposite direction, whatever that direction is in space. But you're doing exactly the opposite. You negate every term. It's the same thing as this, only now your C is a minus 1. So you just multiply minus 1 by everything. So that's all it is. Okay? Now you can define the difference of 2 vectors in space. U minus V in space would then simply be U1 minus V1, comma, U2 minus V2, comma, U3 minus V3, comma, dot, 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 all the way up to and including U sub n minus V sub n. They both have to be in space to add or subtract for that to make sense. Now, what you just did there, whether you realized it or not, if you were subtracting v from u, that's the same as adding the opposite of v to u. If you had done this for v, then, and u would have been up there, then this would have been just like we did with two space any place. Okay. Now, one more thing you need to know is the zero vector in Rn. Now, this is the one time we use a number as the vector name. But you, in the book, they bold it. I can't write bold, so I put a vector arrow over it. And this would be 0, 0, 0, dot, 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 all the way up to 0. You just have n of these because you're in n space. Okay? You have to have n components, and every component has to be 0 to be the zero vector. Now, I said before, you aren't here, to me the zero vector is almost a misnomer because vectors by definition have magnitude and direction. A zero vector has zero magnitude, so it doesn't have any magnitude, and it has no direction. How can you point nothing in a direction? You can't. But you still have to have the definition and the ability to talk about a zero vector. Otherwise, you can't have a vector space. That's an essential part of a vector space. Okay. So, I'm sorry. This cold is driving me nuts. I can't breathe. All right. So now let's go back to simple little 3 space. Here's a vector in 3 space. -1, 0, 1. A pretty simple vector in 3 space. And here's another vector in 3 space. V, and this will be 2, -1, 5. Another relatively simple vector. Both of these are elements of R3, 3 space. Okay? It says find each of the following. A, find U plus V. What would that be? Now, time out for a moment. You weren't here when I mentioned this before. You had Larson's Pre-Calculus Algebra and Trig book, right?
No, sir.
Oh, you did?
No, sir. No, sir. You mean the class itself?
Right.
I took it at UAB.
You did? Oh, okay.
It was, and unfortunately, it was online. So
I see. How
How
about?
touch based on the unit circle. It was just so fast paced.
Right.
And it was summertime too, of course.
Right.
But yeah, it was. I
Did you?
Take it again.
Yeah. Did you have Larson calculus?
No, sir. It was by
Okay.
Dr. Gloria Vaughn. She had her own book for the class.
Oh, I see.
She had some kind of.
Okay, so you took all your calculus and all your.
No, I took pre-cal, algebra, and trig. It was combined.
Right. There.
It is accelerated course. But yes, sir. I took Cal 1 there. But I took Cal 2.
Okay. Well, in Cal 2, you had Larson's book for that, didn't you?
Yes, sir.
Right. And I don't know if we hit that many vectors in there. I think we did.
Yeah, I'm sure we did. Because I think we spent a lot of time on that chapter that we're in.
Right. So in his earlier 2 books I know of, the ones I've taught from, Pre-Calculus, Algebra, and Trig, and Calculus 1, 2, and 3, that's one book, one big thick book. Okay? In every one of those, when he talked about a vector, he put them in angle brackets. It looks like less than sign and greater than sign, okay? Those angle brackets, okay? And that's how he distinguished the vector. But in this text, same author, he puts them in parentheses, okay? So that's why I've been doing that. I'm trying to break myself of angle brackets because that's how I always do it in other courses, but in this course he uses parentheses. Normally if I saw parentheses in the other book, that meant a point in space. -1 on x, 0 on y, positive 1 on z. Okay? It would have been back there somewhere. Okay? But here you have to read it determined by context. This is a vector because it said the vector is equal to that. If it said a letter, capital P, that would be a point. Is that, then it would be coordinates of the point or components of a vector. You can't distinguish by the symbology. You have to do it by context. So, anyway, if you're adding these two together, what would be your first component?
Negative 1 plus 2.
Which is?
-3.
No, it
I
isn't.
mean, positive 3.
No. Negative 1 plus 2.
Oh, 1.
1. Very good. Okay? Second
Well,
component.
0. We know 0.
Huh?
No, it's going to be 1. Positive 1.
No.
0 plus -1. It's going to be -1.
Minus 1. And
1 plus 5 is going to be 6.
it's what?
6.
6. Yeah. Okay. There is a sum of those two vectors. Okay? The B part says, tell me what 2u is. That's as in happy birthday, but never mind. Okay.
Negative 1 times 2 is going to be
Negative
-2.
2.
0 times -1 is going to be 0.
No, not times negative 1, 2, but it doesn't matter. It's still going to be 0.
And 1 times 5 is going to be 5.
Wait, where do you get 5? 2 times u. Okay. Let's write it this way. Maybe this would be helpful. 2u would be 2 times vector u, which is -1, 0, 1. And what would that be?
-2,
Negative 2,
0,
0,
and 2.
2. Perfect. Okay? Now, the C one says, what is v minus 2u? Vector v minus 2 twice vector u. Well, let's spell it out. That would be 2, -1, 5, minus 2 times -1, 0, 1. So let's do it in 2 steps. You don't have to, but let's do it. 2, -1, 5, minus, and what would that one be?
-2,
-2,
0,
0,
and 2.
2, just like we got here. That's exactly right. And now, if we're doing that, what would that give us?
So we're multiplying u times v.
Say this again.
We're multiplying u times v.
Okay, all we're doing is subtracting these two vectors.
Oh, okay.
This vector minus that vector.
2 minus -2 is going to be 0.
No, 2 plus -2 would be 0. 2 minus -2 would be
Oh, 4.
4. Perfect. Okay?
-1
-1.
-0
Yeah.
is going to
Is what? Is -1.
be, yeah,
Okay.
-1.
Okay?
And 5 minus 2 is going to be 3.
3. Perfect. Okay? See how they did? They did u plus v was 1, -1, 6. Perfect. B was -2, 0, 2. Perfect. And C was 4, -1, 3. Excellent. Okay. Now, if some of these look or sound familiar, they should be, because this is exactly what we did for R2, what? 2 pages ago, okay? We're doing the same thing for Rn. Okay? So I'll list them again. They did in the book, so I'm going to list them again. Evidently, they're fairly important. Okay? So let me clear this. All right to clear?
Yes, sir.
Okay. All right. This is theorem 4.2. What we're doing, these are basically identical to what we did a couple pages ago when we were dealing with R2. Now we're dealing with Rn. So what we have is U, V, and W are vectors. Vectors in Rn. In other words, they're all the same dimension. Whatever that dimension is, 7, 14, 8, 45, whatever it is, they're all the same dimension. Okay? And C and D are any two scalar numbers. Okay. My head's so clogged up. All right. And by scalars, we mean any real number. Okay. I hate to do this, but I think I'm going to have to go clear my head. I can hardly breathe. Sure. All right. Here are the properties of vector addition and scalar multiplication in Rn. If you remember on the previous page, okay, or what we just did, were the standard operations, which are just vector addition and scalar multiplication. That's what we're talking about here. But these are some properties of those two standard operations. Okay? And the first 5 are the addition ones, and the last 5, 6 through 10, are the scalar multiple ones. Okay? Just like they were before. So U, V, and W are vectors in space, and C and D are any two real number scalars. Okay? Here's the first one. The sum of U and V, and you saw that in our earlier example, has to be a vector in Rn. Okay? Because if U has n components, V has n components, and you add them multiple component by component, you're going to wind up with a n-component vector, which means it's also in Rn. So that's sort of a duh one, but that title is closure under addition. Okay, another way of saying that, vector addition is closed, in space. You'll see it, the verb close or closure, either one. Okay, number 2. And we did this when we were illustrating adding vectors into space. Same thing holds here. If you do U plus V, that's identically the same as V plus U. And if you think about it, this is U1 plus V1, common, U2 plus V2, common, U3 plus V3, common. And what's this one? V1 plus V1, common, V2 plus V2. They're the same thing, and because the components are real numbers, okay? And real numbers are commutative in addition, so are vectors. So vector addition in space is commutative. So it's called the commutative property of vector addition. Okay, I didn't spell it right, but it's okay. They just say of addition, but we're dealing with vectors here. Number 3, fairly similar to it. If you have U and you add to that V, but then later add to that W, remember that's your third vector, you get the same result if you added U to the sum of V and W. Okay? So property number 2, commutative, says it doesn't matter which direction you add. When you're adding, it doesn't matter. Okay? Number 3 says it doesn't matter how you associate the things. It still adds the same. And if you think it's the same deal, U1 plus V1 plus W1. Okay? U2 plus V2 plus W2. U3 plus V3 plus W. Whereas over here, it's U1 plus V1 plus W1. U2 plus V2 plus W. It's the same 3 numbers, component by component. And because it doesn't matter how you associate them, adding them in the real number system, it doesn't in the vector system either. So this is the associative properties property of vector addition. Associative property of vector addition. Now, here's 4. Now, this is one that you have, this is why you have to have the 0 vector. Because the U plus the 0 vector, guess what that is? U. You don't change it at all. Because every component of the 0 vector is 0. So U1 plus 0 is U1. U2 plus 0 is U2. You get U again. And this is called the additive identity element. They just call it additive identity property. Sorry. They call it property. I would call it element, but it's okay. Number 5. Last of these. If you add vector U in n space to the opposite of vector U in n space, what do you get? Okay, say U1 plus a negative U1, right? So U1 minus U1 is 0. U2 minus U2 is 0. U3 minus, so you get the 0 vector. Same one we had up there. Okay? And this is just like adding the opposite integers together, or opposite real numbers together. Negative 3/4 plus 3/4 is 0. You know, 3/4 minus 3/4 is 0. You know, same thing here. And you have to have, this is why we have to have a 0 vector in order for addition to be closed in vector space. Because if you didn't have the 0 vector, you couldn't add those 2 vectors together. So you have to have the 0 vector. So this is the additive inverse property. Okay, additive inverse property. Okay, number 6. These start our scalar multiplication. The first is that C times vector U is an element in Rn. In other words, since U is a vector in Rn, you multiply each of its components by the scalar number C, you're still a vector in Rn, okay, in n space, okay? So it's also an element of n space. Now, this is the closure property under addition, under scalar multiplication, sorry. Okay, scalar closure under scalar multiplication. Number 7. Here we start getting to be a little picky, but if you have the letter, the number C, real number C, and multiply that by the sum of two vectors, u plus v, in space, then you're going to get, what would you expect? Cu plus Cv. Got it. Okay? And you do each one at a time and you get there. Like here you'd have u1 plus v1, u2 plus v2, u3. You do C times this. That, you're absolutely right. The distributive property of scalar multiplication over vector addition. Okay. Now, they didn't put all those words there. I did. They just say distributive property. And the reason I said a few more is, look at their number 8. It is, what if you had two scalars, C plus D, and multiply that by a vector U? What would that produce? Cu du. Huh? Yeah, that's correct. I was just what I call this is distributive property of vector multiplication. That's not quite right, but over scalar addition. And I'm going to say that here, vector multiplication over scalar addition. Whereas before we were vector addition and scalar multiplication, here it's vector multiplication over scalar addition. Now, it's not important that you segregate those two, but there are different operations. Now, we'll leave that alone. Starting to mention something else, but it would probably get more confusing than it would be worth. Now, here's another one that seems familiar. C times du, where u is a vector, C and D are scalars. What would that be the same as?
Thank you for that.
Huh?
Yeah, parentheses C enclose C D times U.
Yeah. Okay. Now, that is one type of an associative property of multiplication, but you just, to me, you just can't say that. This is associative property of scalar and of scalar multiplication. Let's just say it there, of scalar multiplication. Okay. Now, notice these two have to be scalars, only one vector. These two scalars, only one vector. Okay. And hopefully that makes pretty good sense. Okay. What you can't do is a scalar times the product of two vectors. Because guess what? You can't multiply two vectors that are identical. I mean, identically. This is a tough thing to say properly. You can multiply two vectors if one is a column vector and the other is a row vector. A row vector and this is a column vector, then you can multiply those. You get a single number. Or, if this is a column vector and this is a row vector, you can multiply those, then you get a 3 by 3 or n by n vector. Okay? So you can't just say if u, v, and w are vectors in Rn. You have to specify one has to be a column, one has to be a, and we don't do that. So there is no associative property of vectors alone. Only when you have two scalars, one vector, then you have this associative property. No other instance, okay? At least for now. And then let's do our last one. And the last one is this. 1 times the vector u is what? Vector u. Absolutely. Just like it is with real numbers, multiple, this is just like up here you had an additive inverse property. You add something to it, you get the same thing. You multiply something by it, you get the same thing. This is the multiplicative. Okay. Inverse property. Okay, just don't remember to, okay. All right. Multiplicative inverse, I'm sorry, not inverse, identity. For some reason I tend to cross those words out when I don't mean to. Okay. Identity property. Identity. I let you spell it. The multiplicative identity property. Just like adding 0 vector to a vector, you get the same vector. Multiplying a vector by the scalar number 1 gives you the same vector. It's the multiplicative identity property. Now, difference is, up here you're adding a vector to it, here you're multiplying a scalar by it. But it's the same type deal. Now you'll notice you've already done it, but I'll say this for the others who may be listening or not. You'll see there's a blurb there on William Rowan Hamilton, considered to be Ireland's most famous mathematician. He basically did some of the very earliest work in vectors. I'm not sure he even called them vectors yet, but he did that. Now, if I'm not mistaken, he also extended it into another, you might say, element. And let me think if I can remember what they're called. Tensors or something like that. You have a three-dimensional vector, but then there's another thing that you can have that will do the same effect as dealing with vectors. You just take it up a notch and go to, it's almost like another dimension. Not an n-dimension thing, but one more step up the process. Tensor is what it's called, and let's just leave that alone. I believe he's the one that did those as well. Okay, let's do example 5. Goodness gracious! Don't want to go too much over time. Here we have u is a vector, this time in 4 space. 2, -1, 5, 0. Okay? Vector v. Now, if you're going to be doing anything with these, it better be in the same space. It is 4, 3, 1, and -1. That's a 4 space. Goodness gracious. W. I'm getting worse and worse. Better be 4 space. Yes, it is. Negative 6, 2, 0, 3. All right. Be vectors in R4, R superscript 4. Find x using each equation. Now, okay. Here's the A part. X is equal to, is a vector x, is equal to 2u minus v plus 3w. Yuck. V plus 3w. All right. Man. Now, in my way of thinking, the best way is just plug them in. After a while, you might be able to do them in your head, but to start with, I would plug in. So I would say 2 times vector u is 2 minus 1, 5, 0. It's a good time to check and make sure I haven't copied something wrong. Minus, open parentheses, and then put the v, 4, 3, 1, minus 1, plus 3 times w is minus 6, 2, 0, 4. 3, sorry. I knew something looked wrong there. Number 1, that 0 is an ugly looking 0. Okay, hopefully that's a little better. All right, and then close that parenthesis. So let's start what we can. What's the first stage here?
2 times 2,
4.
2 minus 1 is going to be minus negative 1.
Negative 2. Right.
2 times 5, 10.
All right, 10. Goodness, these marks.
2 times 0 is 0.
Okay, wait just a second. Yeah, 0.
Let me check, let me make sure I'm right.
Say again?
Make sure I'm right. Yeah, that's right, 2 times 0.
Yeah. Now,
Minus,
yeah. Again, let's not mess with this until we multiply. So we're just going to write it down. 4, 3, 1, minus 1. Plus, and that is a plus, right? Yeah. And what would this be?
3, it's going to be negative 18.
Got it?
6
6.
0, 0.
Got it? I'm sorry? Yeah. 3 times 3 is 9. Okay. All right. Now, again, we're going to do this in gory detail. It's safer that way. That'd be 4, negative 2, 10, 0, minus, let's first add what's in the bigger parentheses. What does that give us? Four minus 18 is
14.
minus 14. Right. Okay. Next. Okay, it's not a minus. And it's not a 4. It's a 3 plus 6. Component by component.
Was it 3 minus 6?
No, it's 3 plus 6.
3 plus 6. That's going to be,
You see, this sign is a plus here. So it's this component plus this component. That component was negative, and that's what drug this down to be a negative 14. If both of these are positive, you're adding them. So there's no. Okay. Next.
and 1 plus 0 is
1 and
negative 1 plus 9 is going to be 8.
8. Got it. Now we're ready to do the last step.
18 negative 11.
You see why?
Yeah.
4 minus a minus is a plus, 14 is right
Yeah, I
there.
see it now.
Okay. Next.
Negative 11
Negative 11, perfect.
and
9, next.
and negative 8.
Negative 8 is next. Fantastic. Let's see how the book did. 18, negative 11, 9, negative 8. They got it right. Okay. Now,
We've got 2 minutes. You want to talk about that?
2 minutes? Okay, let's see if we can get B done very quickly. I'm not sure we can, but let's try it. Okay. I wanted to leave the same stuff up there at the top because we're using the same values, and I'd hate to have to write this again next time. I mean, it's not hard, but it's just tedious. Okay. So here's the B part. Sorry, now do you need to get back to work?
No, I'm good.
Okay. All right. This is 3 times x plus w is equal to 2u minus v plus x. Now, you really have a couple choices here. It's kind of like when we're solving problems that you have formulas and you're plugging things in. If you're solving for something that's mixed up in there, you can either solve for the variable first and then plug the numbers in. I call that chug and plug. Or you can plug the numbers in and then solve for the variables. Now, I think it's easier to solve for the variable first and then deal with the numbers. Otherwise, you're going to have 4 equations, one for each component, and you're going to have to carry them all the way through, and it'll get really messy. But let's first solve for the x's. Okay, here the x is by itself, here it's not. So let's first use that property we had, that 3, oh, I forgot to put my vector symbols over, okay? This would be 3 times x plus 3 times w, distribute, right? Is equal to 2u minus v plus x, okay? Now what I want to do is get all my x's together, so I'm going to subtract an x from both sides, and I'm going to subtract the 3w from both sides. Now, you don't have to do this at once, but since we're running out of time, I thought to do this. So this will be 2x, right? 3x minus x is 2x, okay? That goes to 0, is equal to 2u minus v, yeah, that goes to 0 minus 3w, okay? Now, you can either take it one more step and divide by divide by 2 to make it 1/2 of that, or you can wait and do the calculations and then divide by 2. I don't think it much matters in that, which way you want to do it. Do it. Go on and do it. Okay. So divide this by 2, which is going to be dividing this whole thing by 2. Here the 2 goes out. You get x is equal to, and here you get just u minus 1/2 v minus 3/2 w. Okay? That may be a little messy, but I think we can do it. So now plug and chug. Now we plug. We've already chugged. So our u is 2, -1, 5, 0, minus 1/2 of, the v is 4, 3, 1, minus 1, minus 3/2 of -6, 2, 0, 3. Okay? Let's leave this one alone for now. 2, -1, 5, 0. Now, I'm going to make this a plus because to me it's easier to add. Plus, I'm going to take the minus inside here. And what would that be? Half of 4. But I'm going to take the minus into, so it'd be -2. Half of 3 is -3/2, because you take the minus in with that. The next one will be 1/2 of 1 is, but it's a minus, pull that inside. And then the last one is 1/2. The minus changes that to minus or plus. Sorry. It's just because I like to add better than to subtract. So I'm going to put this a +2 and drag the minus sign inside as well. So what will that be? Okay, wait. 2 will go into 6 3 times. Minus 3 times minus 3 is +9. Right? Okay. And 2 will go into 2 once, so this is just going to be a -3. And that's just going to be a 0. I'm not going to put a plus or a minus sign with that one. And the last one's going to be a -9/2. Right? Okay. Here's the advantage of having all the pluses in between. You can just combine like components. Okay? So the first component, here's a +2 -2, that adds a 0. That leaves you just a 9. That was nice. Okay, the next one is a -1 and a -3. It's going to be -4 minus 3/2. So that's going to be 4 would be 8/2. So this will be -11/2. Right? Right. Okay. And then the next one is, 5 minus 1/2. Well, 5 is 10/2 minus 1 is 9/2. Okay. And then the last one is 1/2 minus 9/2 would be -2. No, -4. You're right. You're right. -4. Okay. Because 8/2, which is -4. Yeah. All right, let's see how they did. 9, -11/2, 9/2, -4. Got it. So we'll start next time with, on page 151, top of the page. All right, let's see how far we got. Oh, we almost finished 4.1. I think you could do number 1. It should be found at calcchat.com. 3 or 5, they should also be at calcchat.com. 7 or 9 should be at calcchat.com. Any of the odds, 11 through 15, should be at calcchat.com. 17 should be at calcchat. Any of the odds, 19 through 23, should be at calcchat. 25 or 27 should be at Calc Chat. I think you can do 29. It should be at Calc Chat. Okay, I think 31 should be at Calc Chat. We just did one like 33 or 35. They should be at Calc Chat. We just did one very similar to 37, and it should be at Calc Chat. Let's hold off there, though, and we'll pick up the rest of those later. So only go through 37 now. Now, if some of those get a little hairy, wait, we'll do a few more examples, and they may get to be a little better. All right, sorry we went over, but there's no extra charge.